All right, hey everyone, and welcome. Today we're putting on our detective hats because we're about to become chemical detectives. And what's our big case? Well, it's solving the mystery of what happens when you mix two totally clear liquids and poof, a solid just appears out of nowhere. Now I know it looks like a straight-up magic trick, but trust me, it's just some really cool chemistry. So, here's our game plan for cracking this case. First up, we're going to look at our first big clue. What happens when compounds break up in water? Then, we'll get to the main event, that mysterious solid that just shows up. After that, we'll check out our detective's rulebook, figure out how to tell the real players from the ones just watching, and solve a case together, step by step. And you know what? We'll even see how all this connects to that can of cola sitting in your fridge. Let's get started.
You know, every good mystery has a crime scene, right? Well, for us, it's usually something like this, a simple beaker of water. This is where it all starts. This is where an ionic compound, we're talking something like plain old table salt, gets dropped into the water.
Okay, so when that salt crystal hits the water, it's like a big dramatic chemical breakup. The water molecules, they've got their own little positive and negative ends, and they just swarm the salt crystal. They literally pull it apart into its original positive and negative ions. And this process, it's called dissociation. So now you just have all these ions floating around, free and single.
And now for the main event. So we take two different clear solutions, right? Both are just full of these free-floating ions. We pour them together, and boom! All of a sudden, a solid forms out of what looks like thin air. I mean, how does that even happen? Is it some kind of sorcery? Nope, definitely not magic. It's what we call a precipitation reaction. Just think of it like this. After that first breakup, all those ions are single and ready to mingle. And sometimes, a positive ion from one solution sees a negative ion from the other solution, and the attraction is just so strong that they form a brand new couple. This new compound they form is so solid, so tough, that even water can't pull them apart. And that solid, that is our key piece of evidence. We call it a precipitate.
So how can we predict when this is going to happen? I mean, we can't just be guessing, right? Well, every good detective needs a rule book, a set of essential clues that tells them what to look for. And in chemistry, we have exactly that. They're called the solubility rules, and they're our ultimate guide for predicting when a precipitate will show up. And here it is. This table is basically our detective's cheat sheet. Now, don't freak out. You don't have to memorize this whole thing right now. Just think of it as our guide. It tells us which combinations of ions are going to form that solid precipitate. Those are the insoluble ones, and which ones are going to just stay dissolved and float around. It's kind of like a compatibility chart for ions.
You know, in any chemical reaction, it's just like a big sports game. You've got your players, the ones who are right there in the middle of the action, scoring points, and then you've got the spectators, the ones who are just hanging out in the stands watching it all happen. To really solve our mystery, we have to figure out who's who.
So those ions that are just kind of hanging out, the ones that don't actually form the solid, we call them spectator ions. They start out dissolved in the water, and they end up dissolved in the water. They're literally just watching from the sidelines. The real key to solving these chemical mysteries is to learn how to ignore them and focus only on the action.
Okay, so this is what the whole crime scene looks like at first. It's the complete ionic equation, and it shows everybody who was invited to the party, all the reactants on the left and all the products on the right. It's a little crowded, right? A pretty long guest list.
Now let's find our spectators. It's actually super easy. All you have to do is find the ions that look exactly the same on both sides of that arrow. See the sodium ion, Na+, and the nitrate ion, NO3-? They haven't changed one bit. They didn't do anything, so we can just cross them right off the list.
And once we get rid of those spectators, this is what we're left with. The net ionic equation. Look how clean and simple that is. It gets right to the point. It shows us only the star players involved in the action. That silver ion and that chloride ion teaming up to form solid silver chloride. This right here, this is the chemical highlight reel.
Okay, detective, time to put your skills to the test for real. Let's solve a case together from start to finish. We're going to mix two solutions and use our awesome new procedure to predict exactly what solid is going to form.
And here's our trusty 5-step method for solving pretty much any precipitation mystery. If you just follow these 5 steps, you'll always get to the net ionic equation, which, remember, is the real story of what's happening inside that beaker. All right, here's our case. We're mixing iron third nitrate and sodium hydroxide. Step 1. We write out the whole balanced equation. Then for step 2, we whip out our rule book. And if you check rule number 5, it says that most hydroxides are insoluble. Bingo, we found our culprit. That means our precipitate, our solid, is going to be iron third hydroxide.
Moving on to step 3. Now we just dissociate, or break up, everything that's marked with that little AQ, which just means it's aqueous or dissolved in water. We split them all up into their ions. But look closely. Our solid precipitate, the iron 3 hydroxide, that stays together. Why? Because it's not dissolved anymore. We don't break it up.
Step 4 is my favorite part. It's time to get rid of the suspects who had nothing to do with the crime. We look for the ions that are exactly the same on both sides, and there they are, the sodium ions and the nitrate ions. They're on the left, they're on the right, totally unchanged. They are our spectators. So let's get them out of there.
And there it is. After we've removed our spectators, this is what's left, the net ionic equation. It's just the iron ion and the hydroxide ions reacting to make that solid iron hydroxide. That's the real story. Simple, elegant, case solved.
Okay, so let's take these detective skills out of the lab and into the real world. Like, say, your kitchen. Because these exact same ideas about solubility can explain precisely why your favorite can of soda always goes flat.
So check this out. Here's a really weird twist in the story. For solids, like when you dissolve sugar in hot tea, making it hotter helps it dissolve faster. More heat, more solubility. But for gases, it's the complete opposite. Think of the gas particles like a bunch of hyper kids at a swimming pool. The warmer the water gets, the more energy they have, and the faster they want to jump out. That's exactly why a warm soda goes fat so fast. All the gas is just escaping.
You see, the fizz in your soda is just a ton of carbon dioxide gas molecules that have been crammed and forced into the liquid under super high pressure. And the second you crack that can open, you release all that pressure. That satisfying pssh sound, that's the sound of millions of CO2 molecules making a run for it, escaping into the air as tiny bubbles.
And we're not talking about just a little bit of pressure here. The pressure inside a sealed soda can is more than double the normal air pressure that's all around us right now. That intense pressure is the only thing keeping all that fizzy gas dissolved in the liquid. The moment you break that seal, the countdown to a flat soda has begun. So there you have it. That solid that appears from nowhere, it's not magic, it's a precipitate. And the fizz in your soda, that's all about how pressure and temperature affect the solubility of a gas. So think about this for a second. What about soap? How does that work? Well, it uses these same rules. A soap molecule has one end that dissolves in water and another end that dissolves in oil and grease. It acts like a little bridge, letting the water grab onto the grease and wash it away. It really all comes back to these same fundamental rules of what dissolves in what. Pretty cool, right? Thanks for cracking the case with me today.